In the fourth workbook, we'll be introducing what is linear regression or linear models, and these are the topics we'll go through. Firstly, what is the difference between dependent and independent variables? What does this linear mean? What is regression? What is the error metric between that determines how the line or how the linear regression line should be drawn? We'll be touching a bit on simple versus multiple regression, and the objective is really just to have an appreciation of linear models. So firstly, linear regression is a linear approach to modeling the relationship between a dependent and one or more independent variables. So what then is the meaning of dependent or independent variables? So if we use the example that we had the last time, on me either taking the bus or the train to work, the dependent variable is that of me either taking the bus or the train to work. It is named dependent because the outcome of it is dependent on the other variables, such as did it rain or not, did I oversleep, is there going to be an important meeting that I can't miss. So these other variables, whether did it rain, is there a meeting, did I oversleep, they are known as independent variables. They are independent because the outcome of it is independent of all the other variables in the entire model. For example, whether did I oversleep or not does not affect whether is it going to rain or not. And conversely, even if it rains, it does not mean that I will or will not have an important meeting. So all these three variables are in fact independent of one another and independent also whether I should take the bus or the train. However, the dependent variable whether I should take the bus or the train is dependent on if did I oversleep, did I do I have an important meeting, or is it raining or not. So the dependent variable is always in a way dependent on the other independent variables. So that's really how you think about the difference between independent or dependent variables. Another example that we have over here, so for instance, if you want to model the relationship between income and debt, so you want to predict the amount of debt a person will undertake based on the income, what would then be the dependent variable? It will then be the amount of debt, and the independent variable will be his income. So intuitively, it is natural to think this way because the dependent variable is really dependent on the dependent variable of the taking the amount of debt that a person will take is really dependent on the independent variable of his income. So once again, it is typical for independent variables to be called the x variables, dependent variable to be called the y variables, and it basically because it's usually how they plot it on the graph. So the dependent variable is also the variable that you are looking to predict. So if you look at the multiplication example we saw in the previous workbook, what are the x variables, what are the y variables? So the x variables will be the independent variables, would then be a and b, and the y variable would then be the dependent variable, which in this case is r, and r is dependent on independent variables of a and b. Okay, let's dig a little bit deeper into the multiplication example. So imagine if the model is like this. We have b on one side and r on the other side. The input variables are 1, 2, 3, 4. Output variables are 2, 4, 6, 8. So excuse me. It is really clear that the formula would then be r equals to 2 times b. So would you think that this is considered a linear relationship? Well, evidently it will be, because we have a linear integer that is before the input variable of b that determines the output value of r. How would such a graph look like? So if we plot out the graph over here, So let's try this again. So this will be how the graph looks like. So at x equals to 1, y equals to 2, x equals to 2, y equals to 4, 3 and 6, 4 and 8. Okay. So this will be then the topic of both dependent variables and linearity of variables. So if we go on to the next topic on regression, so we talked about earlier what is classification, what is regression. So regression is the prediction of a quantitative variable based on the dependent variable. So the key phrase is that the dependent variable is quantitative, meaning that it is probably a numerical value. So let's look at some of these examples. A model that plays a game of chess, is this a regression task? Probably not. So the task is to move chess pieces from one piece of the board to another that maximizes a certain reward, and this is typically that for reinforcement learning. So this would typically not be that of a regression. How about the second one? A model that predicts if a person is going to default on his loan. So probably may or may not be, but most probably this will not be. Why? Because I'm predicting if it is a 1 or a 0. So a true or false, whether is he going to default or is he not going to default. So typically in such cases, these are normally structured as a classification problem, so this will not be a regression task. How about the third one? The probability that predicts the probability that he will click an advertisement. So yes, this would then be a regression task because we are predicting a numerical value, a quantitative numerical value, which is a probability term. So this would then be a regression task. How about the fourth one? That predicts yes or no if he will click an advertisement. So this is very similar to the second part, whereby it is a true, false, yes, no kind of a prediction. And typically in such prediction tasks, they are normally termed as classification. The last one, a model that clusters people of similar income levels together. So this is a bit more of unsupervised learning of clustering. So it's not really a regression task. So out of these 5, only the third one is a regression task because we are predicting a numerical value. So another short discussion, what will be the value of the dependent variable? If the independent variable is 23, so of course it will be 46. Following on with the regression model of 2 times b, so the result would then be 46. So we talked about this a little bit in the earlier part of part 3. So we have this training data set. So in this case, the training data set probably will be these numbers of 1, 2, 3, 4 and 2, 4, 6, 8. So this will be the training input. This will be the so-called predicted output labels that the training input should have, and this will be the entire training data set. Do you think this is supervised, unsupervised, or reinforcement learning? So definitely this is supervised learning because we are giving the input so-called input numbers as well as the expected output numbers. So this will be the entire training data set consisting of both the input and the output variables. Okay, next we go on to the error metric. So in the earlier example, we have r equals to 2 times b. But typically when you are provided with the training data set, you don't have the number 2. In fact, you are supposed to predict what is the number, or rather what is the coefficient of b supposed to be, and you kind of find it out through so-called selecting the best so-called coefficient of b in order to minimize a certain error function. So in this error function, or in this error metric that we use typically for linear regression, we use something called the root mean square error. Okay, so we ascertain how good or how bad the model is through an error metric, and in linear regression we do it using the metric known as the root mean square error. So one of the other techniques is definitely we can use just the predicted values and we subtract it by the actual y values. This is known as the residuals. So question, do you want the residuals to be as low or as high as possible? So if your residuals are low, it means that your predicted values will then be very close to your actual y values. So naturally, you will prefer your residuals to be as low as, typically, you can't say as low as possible, but it's safe to say that you want them to be of a significant level that is not too that's low enough. So another popular metric is known as the root mean square error, and it is given by this formula over here. So what is the difference comparing the residual error versus comparing that of the root mean square error? So the residual error is a sum of all the errors regardless if it is positive or negative, disregarding if the residuals are positive or negative. Whereas the root mean square error, you can think about them as you are always able to get the absolute value of the error, and so the root mean square error tends to give a better representation of how accurate your model is. So when we calculate error analysis for linear regression, typically we use the root mean square error. We normally don't use the residuals error that much. We use it just to find out whether is your model suitable, or rather does your data suitable, is it suitable to be modeled as a linear regression model or not. So lastly, we talk about the difference between simple and multiple linear regression. So we have r equals to 2 times b in this example, and this is typically known as simple linear regression, and we are only using one independent variable to determine the value of the target dependent variables. So usually for simple linear regression, we will only have one single independent variable. For multiple linear regression, we will have multiple independent variables. So that is the only difference between simple linear regression and multiple linear regression. So in part 3, we talked about what supervised learning is, and in part 4.1, we talked about what linear regression is. Right here in 4.2, we're going to combine both together to talk about introduction of supervised learning using linear regression. So in the earlier example, we know that supervised learning or linear regression is to model the relationship between a dependent variable and one or more independent variables. So for today, we're going to go through the steps that it takes to train a supervised learning model. So let's take a typical example of recognizing the pattern of 8. So these are the basic steps that we normally take. So there are 5 steps in total. So step number 1, we load the data into Python, or example is Anaconda Jupyter notebooks. We split the data into training data and testing data. We train the machine model on the training data set, and we train it to recognize the pattern of the number 8 with the training data. Number 4, we find the predictions of the model on the testing data set. So meaning that we will run the testing images through my model, and finally in the fifth step I will find the prediction accuracy of the model on the testing data set. So a typical split between the training and the test data set is 80% and 20%. So this is a sort of a typical basic example that you can all follow. As you go along, you will find that we may have different splits of the data set. For example, we may have the training, test, and validation data set, and we may split it in different proportions depending on the availability of data and the size of the data as well. But for purpose of this workshop, we will adopt this split of data for between the training and the test, and it will be between 80 and 20%. Okay, from here onwards, what we will be doing is we will be sort of creating our own data in order to train a linear regression model on it. So what do I mean by this? So we are going to be creating so-called 50 data points, and these 50 data points fall in the range of 1 to 100, and they are arranged in somewhat of a linear fashion, which is I'm going to multiply my x variables with the number 2, and I'm just going to add a random integer from -2 to 2 onto my y data. So it will typically follow a y equals to 2 times x kind of graph, but not exactly because of the randomness that I'm going to incorporate into here. Okay, so I'm going to run this now, and right now you see that I have created 50 data points of x and 50 data points of y. Okay, I print out the shape of x, the shape of y is 50 and 1, 50 and 1. It just means that there's 50 x points, 50 y points. If I find out what is the first 5 numbers of x and y, these will be the values of it. It has been pointed out to me before that since these numbers are random, why do I always get the same numbers all the time? And the reason is because I have programmed it to be of a certain so-called starting values, and I do that with putting on a random seed over here. So once I have a seed over here, it programs my random number generator to come up with the same set of numbers every single time. And so every single time we run this entire workbook, it will always give me the same set of numbers. So it is really to achieve consistency and also to make sure that all the we are able to follow and all the numbers that we get are always the same, and to check that all of us are moving along properly in the right manner. So once again, we have the x data, we have the y data. So notice that the x data in general, it is about twice the number of that of the the y data is in general twice the number of that of the x data. Not exactly 2 times, but in general it follows a kind of a trend. So the first thing we do, steps 1 and 2, we have loaded the data into the Python. So we have now the x data and the y data. Second step, we need to split it into the training and testing data. So we will do it in this fashion, whereby I have 50 values for x and y. I'm going to train the first 40, or rather I'm going to put the first 40 values into my x training, the first 40 values for y into my y training, and I'm going to put the last 10 values of my x into my x test, and similarly the last 10 values of my y into my y test. And when we do a printout over here, we see that this is a size of 40 and 1, 40 and 1, 10 and 1, 10 and 1. So there are 40 values in my X training, 40 values in my Y training, 10 values in my X testing, another 10 in my Y testing. If I plot out my training data, this will be my main, this will be my full data of 50 points. This is what it looks like. If I want to plot out my training data, we can do this. Let's try this. You can tell that these are the 40 values that occur, and in general it still follows like a linear line. If I look at my test data, you can tell that it still seems to follow a typical straight line, and you can tell that there are much lesser values, points that we find in the graph. Basically, it's because there are only 10 points for the testing data. Okay, so we'll be using a library known as sklearn to train this linear regression model. So we first use the sklearn import the linear model, and in particular we assign the linear regression to this variable over here. We will fit the training data into the linear regression model. So using just these 3 lines, we will have created the linear regression model. So if you see over here, okay, and then the next thing is the model will be stored in this variable regr, and if we predict it with my testing data, the predicted values will then be stored in this variable over here. This will be the testing data, this will be the predicted data. So the y test is what we have in my y test over here from the actual data, and my y predicted is the prediction that we will have from the model. The next thing we do is we can calculate the mean square error with this line over here. So the mean square error is 1.429. So it may not make a lot of sense right now, but as we go along, you'll find that what it actually means. So this is the line to install the mean square error calculation if you don't have it, and this is the line to find out what is the coefficient and the y-intercept. So the meaning behind this is this will be equals to y equals to 2.013x minus 0.6704. So this will be the meaning, the equation meaning behind the model of what using linear regression model of y equals to mx plus c. And if you take the subtraction between the testing data and the predicted values, you will get a plot known as the residual plot. And the key thing in the residual plot is to check that there are no strange patterns that occur in the residual plot, because if there is, it will mean that your data does not follow a normal distribution, and if it doesn't follow a normal distribution, then it should not be modeled under a linear regression curve. Normally it should be fine. In this case, it is relatively okay. There's no unique pattern that we see over here. We have a few discussion points. So how will the root mean square values change for the following 3 scenarios? So we have the first scenario whereby it is the same distribution and also the same range. Second scenario is if I have the same distribution, which is still relatively multiplied by 2 with minus 2 and 2 offset, but the range is a bit different. Instead of 100 to 200, it is 200 to 500. And the third one is if I have the same range of 100 to 200, but then in this case my distribution is very different. So I have a logarithm term over here together with so-called another offset that is a bit different from what we have over there. So third case. So how do you think this tree will be the root mean square values of this tree will turn out? So evidently, the first scenario, it won't be that much different. Why? Being that the range is the same, the distribution is the same, so the root mean square values would not differ as much as that of the original data set. How about the second one, whereby I have a different different range, but the same distribution? It is going to be slightly higher, but it's still going to be pretty low in a sense. It won't be that much different from that of the first scenario. But looking at the third scenario, whereby I have a totally different distribution, but I have the same range, the root mean square values would then be very, very big. It will be very large because everything is different. So I'm not modeling the. So when I was creating the model, I was modeling under a specific distribution, and of course, if I'm now testing it with a different distribution, then the model generated, or rather the results generated out from that model, would then be very, very different. So that is why the root mean square error would then be very big, and from here we can concur that the linear regression, the testing data for this, it is not generalizable from the model that we have trained earlier. In the fourth scenario over here, it is different distribution and different range, and needless to say, my root mean square error would then be even larger than that of the different of the ones above.